Hi everyone. Today in this video I am going to say some information about 3D human sensing. This video contains the details about 3D human sensing. First, I will give an introduction about this technology. This technology consists of 3D video, visual hull, photo hull and kinematic structure. The development of 3D video led to the development of 3D human sensing technology. In recent years, it was realized that 3D shape capturing of an object in motion as it is. Since 3D video is captured by using conventional 2D cameras, the object is not required to attach special markers nor wear a special costume. This is the clear advantage against other motion capturing technologies, and therefore 3D video is suitable for 3D digital achieving of human motion, including intangible cultural assets. However, 3D video itself is merely a non-structured 3D surface data are same as pixel streams of conventional 2D videos. We use ordinary 2D cameras for capturing the object in motion. We use multiple viewpoints, or in other words, we can say we capture the motion of the object from different angles at the same time. As we require multiple viewpoints to render the 3D object. To render the conventional 2D video to a 3D video, we may need to record the same content from different angles, and hence we get multiple videos of the same object. And from this video, we may focus on the object that is in motion. 3D video. The term 3D video or a few viewpoint video includes two different approaches in literature. The first one is a model-based approach, and the second one is an image-based approach. The model-based approach reconstructs the 3D shape of the object first and then render it into a 3D shape or 3D video. In the image-based approaches, it interpolates a 2D images at a virtual camera position directly from a 2D multi-viewpoint images. In the first method, we need to create a 3D object, and from this 3D object, we render it into a 3D video. In the second method, we use image instead of 3D objects. We may require free viewpoint images, that is, we require the images from different angles of the object at the same time. For example, an object in motion, we need to capture the images of the moving object from the side, front, top, left, right, rear, etc. Model-based approaches are suitable because image-based method does not produce much information about the 3D structure of the object. We have to manually correct the information. This is a drawback of image-based approach, as the edges of the object does not get a clear as from a 3D object, as compared to a 3D object. We get irregular surface of the object in image-based method. The 3D shape estimation is done in the model-based approach. This is a classic one, but opens problems in the computer visions. We get more information about the object in model-based approach rather than the image-based approach. 3D video capturing flow diagram. Here, first we capture multiple images of the object from different angles. It is also called as the multi-viewpoint images. That is, 2D images of the object is captured from various angles. And then from these 2D images or multi-viewpoint region is obtained. It is a black and white photograph of image captured of the region. The colored white region is the object region and the rest is colored as black. From this multi-viewpoint object regions, we get a visual hull of the object or a 3D structure of the object. This 3D structure may be irregular and even the edges are not clear or rough edges. This rough edges and irregular structure had to be smoothened and to be optimized. Then we get an optimal 3D surface of the object. Then later we map the structure texture on the 3D surface. These are the steps followed in capturing flow of a 3D video. Visual hull. A visual hull is a set of multi-viewpoint shieldouts given by the multi-viewpoint object region. These images produce a rough estimation of the object shape, called a visual hull. As we have already said, a visual hull is obtained from the multi-viewpoint object region. The object region and the outer region is separated, and the object regions are combined to form a 3D object. The visual hull will be refined based on the photo consistency between the input images. Texture mapped 3D surfaces can produce virtual images from the arbitrary viewpoints. This is an ill-posed problem to estimate the original 3D shape from its 2D projections. Photo hull. The practical algorithm which integrates conventional stereo matching and shape from chill-out techniques to produce full 3D shape as a photo hull. Assume that we have the optimal photo hull of an object, and we use it as the 3D real surface of the object. Kinematic structure estimation from 3D video. The input is a time series of 3D surface, and we build up the kinematic structure purely from the input data. Let MT denotes the input 3D surface at a time t. We first build the regraph of MT. Regraph is computed based on the integral of geodesic distance of MT and gives a graph structure similar to the kinematic structure of the object MT. This is the figure which is showing the kinematic structure estimation. In the first figure, it shows the segmentation mesh. It is the surface segmentation based on the integral of the geodesic distance. The second one is the REAP graph. It is the preliminary kinematic structure. From the preliminary kinematic structure, the PERG graph is produced. PERG stands for the pseudo endoskeleton REAP graph, and from it, the final unified kinematic structure is produced. The definition of REAP graph does not guarantee to all the graph edges pass inside the MT, and some of the edges may go outside. We modify such parts of the regraph to make sure that it will be engaged by MT. The modified graph we call PERG, the pseudo-skeleton REAP graph. Starting from building the PERG at every frame, then we select seed PERG which have no degeneration of their body parts. Use a simple algorithm that a seed PERG should have 5 branches since we focus on human behavior. It may be like the structure of a skeleton of a human body. Then do PERG to PERG fitting from seed frames to their neighbors. We deform the seed frame so as to its neighbors and we repeat it until the fitting error exceeds a certain threshold. This process gives topologically isomorphic intervals for each seed frame. In each interval, we apply node clustering to find articulated structure. We integrate articulated structures estimated at all intervals into a unified kinematic structure. The final unified kinematic structure estimated purely from the input of 3D surface sequences. This is the figure showing the node clustering to find our articulated structure. The first figure shows the shape structure. It represents the outer edges of the object. The second figure shows the node's motion. From this figure, we get the flow of node's direction, or we get the motion of the nodes. In the last figure, it is the combination of both the shape structure and node's motion together to get the articulated structure. The node's motion is placed at the center of the shape structure, so we get a smooth motion of MT. By increasing the number of nodes also we can form a smooth motion, and also we require more frames to form the initial position to find the final position to get a high articulated structure. And the conclusions are: we introduce human activity sensing algorithm from 3D video. The algorithms we covered are global kinematic structure, complex motion estimation, These all are non-contact sensing and do not require the object to use neither a special marker nor a costume. This is the clear advantage of our 3D human video based sensing.